Mm, okay, it's pending. Yeah, it's fine. Now it's good. Okay, so I just show you the TOV and SFO cases. To some extent, we have talked about the TOV cases, right? Like the last class.
Yes.
So I just want to give brief on each and every cases what we have did, and we have 25 cases totally for the project. Like so you know the SLE, right? So you are aware of the
Yes.
SLE.
Yes.
Yeah.
I am
So
aware. Yes.
we have 25 cases for TOV only.
Okay.
So generally the cases will be like the cases number will be increased if you want to do a TOV or SFO, because since you have to simulate all the possible cases.
Mhm.
So that is important. So you cannot just left over some cases, because since the case is 25, you cannot left over. You can't leave other cases also. Like you have to perform all possible cases,
Yes.
and even sometime client will ask to perform some other cases. So for example, if you I have a 220 kV site and I have a cable at 220 kV.
Yes.
For example, I'm not going to do this Ferranti effect at 220 kV. The client may ask us, so you have to perform a Ferranti effect on the 220 kV, and I want to see the results.
Yes.
So something like that. So that you should ask first. You should ask the client. So is there any requirement from them? Generally, they will tell you the requirement. If they are not going to say the requirement, then you have to perform all the possible cases.
Yes.
So not only TOV, even for SFO, switching front door voltage, or TRV, or FFO, everything, like you have to perform all the possible cases, and you have to report them. So what is happening, like you have to say that no matter what happened, your system will try to recover, or it has some danger or something like that. So based on the results, you have to tell them. So in our project, like in this the SLE which we have shared, that's one kind of project we are working on. So we have totally 25 cases. So all the 25 cases we have tabulated. I just show you the results. So this is the result. Like for all 25 cases,
Yes.
this is the result. Like since it's an TOV, so we have to show the peak over voltage and the RMS over voltage.
Yes.
So can you tell me why you have to show the RMS? Any idea on that?
Because of the rating of the surgeries, the RMS.
Exactly. Yeah, exactly. So if I say, for example, I just show you the so this is one of the surgeons or data sheet. Like Tri Delta is one of the manufacturer.
Yes.
So yeah. So today Venkat have explained you
Yes.
some.
Explain. Yes. Yes.
Yeah. So if I say 336, or if I say rated voltage, whether that is an RMS voltage or peak voltage.
That's a peak voltage rated.
Oh, okay. The rated one is the RMS voltage. That's not a peak voltage.
Or this one. Yes. Right.
Yeah, this is RMS voltage. We can't say that is peak voltage.
Yeah.
And the temporary voltage is for 10 seconds and 1 second, whether this is RMS voltage or peak voltage.
They will be RMS too.
Yeah, exactly. They are RMS voltage.
Yes.
So you should have a clear understanding. If I say 6 kV surge arrestor, that if that's a rated voltage, then the 6 kV is the RMS voltage. Whether the 6 kV is the line to line or line to ground.
That's line to ground.
Yeah, just a minute. Just a minute. Sorry. Yeah, okay. Sorry. Yeah,
Yes. Yes.
fine. Yeah. So that is line to ground, right?
Yes.
So exactly. So your understanding is correct. So
Yes.
if I say a 6 kV rated voltage of 6 kV of a surge arrestor, that 6 kV is line to ground.
Yes.
So basically, if I say 400 kV, my system voltage is 400 kV. Whether that is line to line or line to ground.
That's line to line.
Yeah. So the output from the output from the this is the output from the PSCAT 337.690.
Yes.
So this is line to line or line to ground. The output from the PSCAT.
The out from PS card would
Yeah.
be that would be line to line.
No, that
Oh, sorry,
line to
line to
ground.
ground. Ground.
Yeah.
Yes. line to
Yeah,
ground
that
peak
may
voltage.
yes, that may be kind of confusing, but that is line to ground peak voltage.
Yes.
So since this is TOV and we have to compare with the surge arrestor capability,
Yes.
we are going to change the peak over voltage to RMS over voltage.
RMS. Yes.
So this is 238.769. We should compare this voltage with the
RMS.
10 seconds or 1 seconds voltage of the TOV.
Okay. But
So you yeah.
is it not right that we only compare that 1 second and 10-second voltage with surge arrestor rating in case of fault only?
Okay. So if you say fault, that may only persist in my system within seconds, right?
Yes.
So you just try to like close the breaker, or you just try to you just try to open the breaker and just clear the fault.
Yes.
So it may have impact only on 1 second.
Yes.
So if I have a case, for example, I just take the cases of TOV. Just a minute. Yeah, this is the cases. Okay, okay. So let me take any fault case. Yeah. So case 4 is the line to ground fault. So
Yes.
for this case 4, I have to compare with 1 second.
Yes.
Since because that is the fault may only have a precise in my system only in for 1 second. Like it will not. We don't allow this fault to more than 1 second, right?
Yes.
So in simulation, like that will be different, but on real time you will not like allow the fault to be in my system more than 1 second.
Yeah.
So the value from the fault, the RMS value from the fault, you have to verify with this value, like u 1 second.
Yes.
And this 10 seconds, do you have any idea on what case I have to refer from this, or have to compare this?
Uh, that will be that will be again fault, but with load rejection.
Yeah, a load rejection and what say load rejection and Ferranti. Just
Yes.
a minute, Sinna, I'm just getting a call. 1 minute.
No problem. No problem.
Himanshu, hi.
Yes.
Sorry.
Yes. No, it's fine. Fine.
Okay. So the thing where we are talking about, yeah,
10-second rating.
yes, U10, yes. So the U10 should be compared with load rejection or with Ferranti effect. Like Ferranti effect, you can't say that it will be less than 1 second. Like it may be more than 10 seconds also, right? So
So we would compare UC, right? Continuous operating voltage with Ferranti. Is that right?
no, with U 10 seconds.
And where we compare this UC?
like we don't compare UC. That's a value called continuous operating over voltage. Like it's a continuous operating
Okay.
voltage. Like we
Okay.
don't compare anything from UC,
Okay.
but the comparative thing in TOV, like they have like clearly they have mentioned only this two tab for TOV.
Yes.
So this is for U10, U1 for only fault.
Fault. Yes. And
Yeah,
U10 for
this
STD state. Yes.
yeah for load rejection or for Ferranti.
Yes.
So are you
Not with the load rejection due to fault, right?
like you can compare this value, like you can compare this.
Yes. 1 second.
Yeah,
Yes.
yeah, 1 second. Like so, do you have any clarifications on this part?
No.
Yeah, because this is important. You should know where to compare, right? So you should know this,
Yes.
and
1 second
this
for
this
fault and 10 second for STD state, like only Faraday effect.
Ferranti and load rejection.
Yeah, load rejection. Yes. But
Yeah.
if there is a
So
load rejection with a fault, then go back to again 1 second on
yeah,
fault.
again, you can go back to 1 second and you can just compare it.
Yeah. Clear.
So,
Clear.
so this is the basic overview of why we have to do the TOV and on what reference we have to verify it.
Yes.
And the thing is, sorry, yeah. So let me talk about the TOV cases. So actually we have talked about, but I just want to just give some brush up this basic things. That's it.
Yes.
So the same thing. Let me open the SLD first, and we can talk about that. Just a minute. Yeah.
You have your dinner or not yet?
No, no, not yet, not yet. Like it's seven
Yeah.
seven twenty over here. So it takes some time. Like after 9, we used to have dinner.
Okay. I have now bad habit because I do early dinner here because there's nothing else to do. So do dinner, you know.
Okay. Fine. So yeah, this is the system. Like this is our SLD, like
Yes.
the SLD which we are going to talk about.
Yes.
And as I said, like we have G30 is cable. Like just give me 10 seconds. Like I have a pen edit. So this is cable.
Yes.
This is OHL,
Yes.
and again this is cable. This is OHL,
Yes. One more OH.
and again this is cable. Like these things are spare. Spare. We don't need to model the spare. Like we don't want to model the spare because that's in future. So our scope only the present thing. So we are going to only model the present actual scenario, which is the cable and this is the OHL.
Yes.
So yeah, so this is one like this 1.5 scheme. Like starting class, Mr. Ramesh would have
Yes. Yes.
explained you what
Explain
is one and a
briefly.
half and
Yes.
yeah.
Yes.
So yes, so the basic thing is, do we need to model the 1.5 breaker scheme in SFO or TOV? So that's the basic thing.
Yes.
Like TOV you can model if you want, you can model, but SFO there is no need to. There is no like no standard I've said to model this kind of detailed model like manner. So I just show you an SFO. I'll just show you
If we don't
SFO.
model breaker in SFO, how we going to do the switching then?
No, no, we have to model the breaker, but the whole one and off scheme I'm trying to.
Oh, the overall, right,
Yeah,
including like
yeah.
isolators and everything.
Exactly. I don't need any isolator. I don't need any bus,
Ah,
like what's the disconnector and everything. Like I just need the what to say. I just need the breaker. That's more than
yes,
enough. I need a source and the cases whether that's an OHL or cable or whatever maybe. The like the corresponding equipments I need. I
yes.
just show you. That depends on person to person. Like, sorry,
Yeah,
that depends.
sometimes folk want to prepare one model and just do
Yeah,
everything with that.
yeah. So sometimes like that, if I take this one model, I can use for all the systems.
Yes,
So you get the point, right? So I'll show you the another model. Like we have, I'll just show you this 220 kV. That depends on person to person. Like I will not model the entire thing because it takes some time, right?
yes.
So you can just model the thing which you want, whether OHL or cable or whatever it is. Yeah, something like that. Like I'll always recommend this to, like personally, I will recommend this. So see, this is 220 kV. Like you can see, like 231,
Yes.
220 kV source. This in 220 kV, the cable, which is basically this is a transformer energization. Like you can see the 220 kV transformer ENER, which is energization. And
Right.
I have only the breaker. I have only the cable. Through cable, I'm going to energize this
Yes.
because in 220 we have only cable. We don't have OHL.
Yes.
So I can show you that. Just give me a minute. Yeah. So okay, over here. So we have a cable one, like this is
Yes.
220 kV,
Yes.
cable two, and we have a only cable over here at
Yes.
220 kV side. If you have a OHL, then you have to add another case with OHL.
Yes.
Like what I'm trying to explain is with cable we have done the transform energization, and with with OHL we have to do another case.
Yes.
So that's the system. Like so I always recommend this model because it will not take more time.
Yes.
And
And rest of the equipment and stuff, it doesn't matter here, right?
yeah, because anyway the circuit breaker is going to get closed.
Yes.
So I'm going to close the circuit breaker. Like so why we have to model that? So that's what
Yes.
I'm trying to explain. Like for example, this is 400 kV cable energization.
Yes.
So cable, then this is cable.
Yes.
So see, these things are off, right? One off. Like if I say one, then the circuit breaker is off.
Yes.
So zero, then it's closed. Like that's the thing. See, only this I have given the breaker logic.
Yes. Cable.
So remaining thing is zero. Like the remaining thing is not in the picture.
Yes.
So why unnecessarily I have to model this?
Yes.
But the advantage for this is only one model you can do like a
Multiple
lot of
steps.
simulations.
Yes.
So if you want to model something like this, yes, of course you can model. There's no wrong in this, but it takes some time. If you
Okay.
correctly model only one system, then you can just give us save project as, and you can use multiple times with different configurations.
Yes.
So
When you are talking about the cable energization or transmission line energization, right? What,
yes.
how exactly you are energizing it and what output you are like getting from it?
Yeah, I'll show that. I'll show that. We have the plot, or I will just like in front of you. I'll do that, and I'll show how the plot look like. So that is
Okay.
important. That is important. We should know whether our result is right or wrong, at least something like that.
Yes.
To some extent, we should know that. So this is cable energization. Like I will come to later. I will come to that plot and everything. Like
Okay.
before,
Okay.
just finish it. I just want
Yes.
to finish the cases.
Yes.
So you understand the point, right, Himanshu? Like whether you can go for this model or you
Yes.
can go
Almost.
for the that model, but it depends on you. It depends on you how you want to model it.
We would
So it
like to model the full thing only if another transformer is like energized there and you want to account the thing called sympathetic inverse. Is that right?
ah, ah, okay, yes, yes, yes. So the interaction between the other transformer
Yes.
also,
Yes.
that
Yes.
is right.
Yes.
So that's good. That's good. Yeah, you can do it. Yeah, fine. So
But if it's a new system, then of course they will energize the transformer one by one. Eh?
yeah. So like I like this kind of modeling because it doesn't take a lot of time.
Yes.
So just like that you can do it, and this is multi-run also. Like it takes some time to just
Yes.
run.
Yes.
So the modeling you have to do it quickly so that if you do any error, you can just recheck it and you can do it.
Yes.
So if I take this system, then I have to like each time I have to like be caution on the circuit breaker whether that is closed or open. Like
Yes.
I,
Yes.
I
Yes.
have
Yes.
that issue.
Yeah.
So only this one is closed and everything is open. Like,
Yes.
so only this one is closed and everything is open. So I don't want to get those kind of like confusions while doing modeling.
Yes.
So
Yes.
I'll always recommend that, but it depends on you. Like finally, it depends on you because you are
But
the
but
engineer
but
to the
uh,
project.
but uh, technically it doesn't matter unless you want to factor in other transformer, right?
Yeah, exactly, exactly. It depends on how the system going to be and how you're going to model it. And
Okay.
if you find any difficulties over here, you can just switch on to this model also. But depends on how the system is and how you're going to model it.
I think this is the easiest study ever. I think people do like transformer and energization, because I never done it, but I have seen like just anyone can do it, like kind of thing. A good
Mhm.
guy or average guy
Yeah.
or
Yeah, but the thing is, the tricky part is you should know whether the model is right or wrong. Whether by seeing
yes,
the, you should be able to say that yes, the result is right. So that is important, and that comes only when you are doing 2 or 3 projects
true.
and you have some
Yes, yes,
that like the background knowledge on that.
yes.
Yeah. So let me go to the Word file and I just. So this is TOV. So the case one is Ferranti effect, like which is we are always talking about this case one, like this 30 kilometer double circuit, and we have done a Ferranti effect. And this case two is again like Ferranti effect, but the issue is we are not going to take the cable over here. So the case one, we are taking the cable,
Cable, and
like
case two, no cable.
that's in service.
Yes,
But here the only the
overhead
30
line.
kilometer thing is in service.
Did you get any difference in that? Like,
Yeah, of course you'll get some difference. So if you want, I can show the results also. I have the results with me. Uh, yeah.
that was
Mhm.
like huge or little?
It was over here like case. Slight change for the case one and case two. There are some slight change.
Yes, there's
So
a good change. Yeah.
yeah. So yeah, when you go to RMS, there will be a good change because it will not come. It will not take the peak value.
Yes.
But when you go to peak, like there is some like zero point 0.5 or something like that.
Yeah. Yeah.
So there is some difference. So because the OHL is not in the picture, right? So
Picture.
sorry, the cable.
Cable. Cable.
Yeah,
Yes.
yeah. Sorry for that. Okay. Then the load rejection. So the thing is 1000 MVA 0.95 power factor. So this like yeah, as Venkat said, you have to get it from the customer.
Yes.
So you have to get it from the customer and at 0.95 power factor. So you have 1000 MVA, but in PS card we have to give per phase, right? Like divided by three.
Yes. Yes.
So you have something like that. So that's a modeling like issue, but the thing is you can just take the 1000 MVA at 0.9 power factor and you have to convert it per phase and you have to just give it like and
Yes.
this is both are in
Service.
like the 30 kilometer double circuit like and in service.
Yes.
Here is and Salaya, which is the this is the LG. This is LG fault with road rejection. Like if there is a fault, and I'm going to clear that fault, and the same time that there is a load rejection. I'll just show you the case for this, the BS CAD model for this, so that you'll get a good understanding of that. Case four, I'll just
The
show you
case
that.
the case three will be like just a load connected and then you just disconnect using circuit breaker, right?
Yes, exactly. Like I'll show you that. I'll show you that. I'll show you that. Like not an issue.
Because once I complete this, I am going to go through all videos again, and I am trying to create some, notes or regenerate the sum of the result, and that will give
Oh,
me some great level
yeah.
of confidence. At the moment, I can't do it because, I mean, I do the video and I try to do the homework and small
Mhm.
exercise, but not
Okay.
like everything because, well, I'm pretty much hell busy in office life. But
Oh, okay. Yeah, I can understand that.
yeah,
Fine. This is case three, like 400 kV SSB substation, like load rejection.
yes,
So only the OH is going to come into picture. So this is one, right? So one
yes,
means it's normally closed. Like it's
close,
like
stable.
starting it may be kind of confused, but like after that you will get the point. Like what is the meaning of one and zero?
One is on in another place, but for this circuit breaker is opposite.
Yes. So if you
Okay.
feel this is I can't understand this, then I'll give you another remedy for that. Take this take this
Breaker logic.
time.
Yes,
Yeah.
yes, yes, yes.
Just give it over here and just give it normally open. That's it.
Okay. Yeah, yeah.
So I can just give you I can just do that. Just
I will
so
get there soon. I think it's going all right.
yeah. So if
Not
you have to just give this one and you have to just
yes,
give open.
yes,
And at the time you can just give more than the duration of time, let's say 5 seconds,
yes.
then it will not close at all.
Come in the
So something like that.
yes, yes, yes.
So if you feel this is kind of tricky and confusing,
No, it's not confusing. It's just a matter of going through this thing again and again and doing
Yeah.
project again and again.
Yes.
You know, now you are teaching me, so at least I know something and I have some experience in the industry. When I
Mhm.
started CDEX, I
Mhm.
have no clue about like what is earthing. No clue. The only is like some definition I studied in uni, like you know a system earthing and this earthing and that earthing, and that's all.
Mhm. Okay.
But now I am doing the job in a good way, so it just comes from the experience. I can't become
Yes.
like you in one day.
Exactly, but yeah, always the like if you have done 2 or 3 projects in insulation coordination, then you would be an expert in insulation coordination.
Well, I am going to do this project. At least like you are sharing me these diagrams and everything, so doesn't matter if I get time like just now or in 1 month or in 1 week. I am going
Mhm.
to do exactly same like you, like seeing these videos, and I'm assuming these video will be there for long time.
Yeah, yeah, of course, that will be there. Like you can't download, but at least you can
Oh, no,
view it.
no,
That
I
will
don't
be there.
intend to download. I
Yeah,
just wanted to see. Yes.
fine. Okay. So this is the case third, which is sorry, like load rejection. What I'm going to do is just going to reject a load
Yes.
at 0.4 seconds. That's it.
Yes.
So I want to ask a question for you. Like, why you have to open at 0.4? Why not 0.2 or why not 0?
That's
Why
zero.
have to why particularly have to open at 0.4? Why not 0 or why not 0.1? Can you just answer me that? Like, I just want to ask you.
You want to do that on a zero crossing after a cycle of.
No, no. Like I just run this. I'll let you know why generally we used to do that.
Okay.
So actually, we talk about this on the fault or on source modeling. I think so. I just forgot that. Like, fine. I'll just repeat that. Not an issue.
Okay. I will maybe remember this.
Like in TOV, that would be kind of important thing.
Yes.
So yeah, that's why I'm just trying to explain that again and again. Fine. Let me take this crosser from 0 to 0.1. What is the voltage at 0.0, 0.1?
That-
274, right?
Yes.
So this is 400 kV system, and this is the peak voltage, peak value. So
Yes.
at least it should come like 376. That is the value, right? If you
Yes.
just multiply 400 divided by root 3 into root 2, you get 326.59.
Yes.
So, but if you just look at this, you're just getting only 274, which is not even 400 kV.
Yes.
So if you convert this to line, it will not be 400 kV.
Yes.
So and even at zero, like you will not get it. I'll just
You
show
were
you.
you were saying like the source take time to ramp up. Is that right?
Yes, exactly. And you have to wait. My system goes to steady state.
Now I remember. Yes.
So it takes some time to go to steady state. The same thing we just explained on load, right? So
Yes.
there will be some peak, and we should not look that. And
Yes.
we
After
only look.
once it attend the new steady state.
Yes. So that's why the switching actions and everything is after the steady state.
Yes.
So you can go like you can give 0.3, that's okay, or you can give 0.4, that's okay. So
Okay.
that's why we have given 0.4.
Yes.
So I'm just going to reject this load, and you know how to do this load and everything, right?
Yes.
So
Yes. Yes.
there is no confusion. Like this
I
1000
have.
MVA 0.5.
Yeah. I have written those formula. Yes.
Yes, that's good. So basically
I
this
am
is
quite poor in formula.
okay. Okay.
I have written them. Yes. Well, I
Fine.
don't do the power system analysis. That's the reason.
Uh-huh. Fine. Yeah. Oh, okay. I understand that. Like, so since this is TOV, we should check the RMS. So that's why there is a need. That's why we have given the this block. This is the
Yes.
RMS block. So since like you can check at 0.4, I'm going to switch the circuit. So you can check that at 0.4, and after that, like there is some like deviation in my circuit in my system. So I can just check it, and after 0.4, I have to check it like
Yes.
0.5 to 1. So the over voltage is 344.
Yes.
So generally we will not check even the same thing in TOV. We will not check at the instance.
Yes.
We will take some time the system to reach a steady state, and we will check the over voltage.
Yes.
So TOV is kind of different from other studies. The SFO and everything, we will measure the voltage from the instance,
Right from
but
instance.
TOV, we will measure the instance at steady state, or we'll give some time to we'll give some time to the system, and we will measure the voltage.
Yes.
So that's the biggest difference between the each studies, like biggest difference between the TOV and other studies.
Yes. Yes.
So TOV is a basic study. We don't need like a powerful tool or something like that. Like this is basic study, and it has some rules and regulations like that. So
Yes.
this is case 4. So you are asking about the case 4, right? Like I'll show that.
Yes.
So case 4 is 30 kilometer 400 kV load rejection with the fault FAU.
Yes.
So I can explain that. Like I just show you what is the case. So case 4 is LG fault with load rejection. I will send this like word file. You can try this.
Yes. Yes.
I
I will
I will
definitely
send
do it.
yeah, that's good. I will send this also.
I
So
will
you can,
definitely do it. Yes. I will. I will play with these things and I will try to generate the results. Yes.
that's good. That's good.
Yes. The most dangerous thing I found is transformer because I dealt it like so many years back and I don't even remember like simple basic formula. So
Mhm.
yes.
Yeah, or transform is kind of a thing. Fine. So what is the basic would say the basic theory behind this is
Yes.
I'm going to apply a fault at 0.4 second.
Yes.
So I'm not going to clear the fault. So
Okay.
duration fault is 5 seconds. I'm not going to clear the fault. Uh,
Yes.
in in TOV, if I say a fault or LG fault or triple LG fault, I'm going to just apply the fault. I'm not going to clear the fault.
Okay.
So I'm just going to leave the fault as it is. But in real time system, they will clear the fault, right?
Fault. Yes.
Yeah, they will, of course they will clear the fault, but in simulation we will not clear the fault, and we will check what is the worst case voltage. If you clear the fault, the voltage will not be worst case.
Yes. It will recover again.
Yeah. So the 400 kV, it will again recover to 400 kV. But the main point of simulation tool is to find the worst case. We are not going to find the best case. We are going to find the worst case. And how we get the worst case by not clearing the fault. We just leave the fault as it is.
Well,
At
we
zero.
just want to we just want to see that for that particular fault duration, what happens as a
Yeah.
maximum volts, and we want to see that maximum volts in a plot. That's why we are
Hmm.
keeping the fault there, right?
Yeah. We're not
In
going
in
to
a-
clear.
in in other words, we are just extending the fault duration.
Yeah, exactly. Yes. So at 0.4, I'm going to clear, like open, I'm going to give an insert of fault,
Yes.
and at 0.5, I'm going to reject a low. So what the meaning of this is, I have a system.
Yes.
Let's take a paint. I'll try to explain it.
Yes. The fault happens
So
and the load side breaker opens.
ah yes,
Screen.
exactly the same thing I want to explain. Like this is source,
Yes.
and this is a bus.
Yes.
Let us assume this is a transmission line, and
Yes.
there is a load over here,
Yes.
and there is a fault here.
Yes.
So at 0.4 there is a fault,
Yes.
and at 0.4 there is a load rejection.
Yes.
This circuit breaker is just going to trip off. That is the main thing we are going to like simulate that. So and then you can check the over voltage. I'll just run this.
Okay.
So the benefit of RMS voltage is also I'll let you know that why. So you can just use this RMS voltage also.
Okay.
Let it run. Yeah. See, the benefit of RS, like this RMS voltage, you can see one phase just goes to zero because this is an SLG fault.
Yes. Yes.
So you can just check it. Fine. The plot or the result is correct.
Yes. Of course. Yeah. Yeah.
Just
The voltage on that phase will be
like
zero and current will be
so
high.
this is this I'm showing the first phase, like the A phase, because that is the fault. So
Yes.
it just goes to zero. The voltage is lesser. So if I just go to B or C phase, then you can see the
Yeah, they are
voltage.
higher. Yes.
So the C phase voltage is higher. So this voltage you have to show to the customer.
Okay, highest one. Yes.
Yeah, the highest one. Always the highest voltage you have to show to the customer.
Yes.
And the things which you are going to tabulate is the highest voltage.
Yes.
So do you have any doubts on this case?
No.
Yeah.
Yes, easy.
Then the case 5 is again the LG fault, but
Yes.
here both the OHL and this thing, the OHL and the cable is in service.
In service. Yes. So we
Yeah,
own the all the breaker and we do the same again.
yeah, the same thing, the same whole thing we are going to perform, but different configurations.
Yeah. Rest of the
This
scenario
always,
are pretty much same, isn't it? Like
yes,
on
yes,
off,
yes.
on off. Yes.
So the same 0.4 second and everything is same. Only the thing is I'm going to take the 16 kilometer cable.
Yes.
So that's the only thing I'm going to differing from the previous case. And the LLG fault again, like the LG and LLG have been simulated for the same system. For the underground cable are in service. So this all 25 cases or something like this. So it has a load rejection, it has a Ferranti effect, and it has an fault initiation. So,
Yeah.
but different configurations, because we have a system with the OHL and cable. So
Yes.
with different configurations, we have to just show it. So
Okay.
I can show you any one case in 220 kV. So these things are 400 kV.
Yes.
Since we have 200 like 400 220 kV is on scope, so we have to check that. I'll just show you the 220 kV also. Any one case. Fine. I can take this load rejection
Yes.
at 220 kV. We took 515 MVA.
Yes.
A 0.94 factor.
Yes.
So these are the things we done for TOV. So you have any doubt on this TOV cases?
No, not at all.
So fine, let's go. Okay, just see this. Yeah, I'll just send it to you. Okay. So can we just move to SFO cases? Yeah.
Yes. Yes.
Before going to it, I just want to give some theory, basic theory on this.
Yes.
Just give me a minute. I'll just open my document. Just a minute.
No problem. No problem.
Uh, yeah. I should have explained before, but I just forgot that.
No, 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 it's fine, mate. We all have some level of stress. We forget the things.
Yes,
When
exactly.
when when we grow adult, our understanding become good, but our memory become weak. And when we are young,
Yes.
our understanding is weak, but our memory is very sharp.
Yes. Fine. Okay. So this is the like if you go to IEC 60071.
Yeah, yeah.
So this is part four. Like there are different parts in IEC 60071. So there
Yes.
are totally four parts. Like previously it has five parts, but the third part is withdrawn. So it has only four parts.
Yes.
So IEC 60071 part four gives about the like how to what say how
Model.
to do or how to model the system, like
Yes.
how to model the source, how to model the OHL and everything.
Yes.
So it like for each study how to model it. So it will just give you the overall picture of that. So here in one of the table they have given something like this. So this is important. So if you want to like generally if you're going to attend an interview or something like that, like they will ask this question. So
Okay.
this is system voltage. Like
Yes.
okay, I can't use the pen over here because it
Yeah.
is protected.
Yes.
So I'll just try to explain this. If you just like if you have a pencil and if you just like draw a line over here, you just go to nearly 1 per unit, which is that the
Yes.
system voltage, which
System
is
voltage.
400 kV.
Yes.
So the temporary old voltage will always like lie between 1 to 2 per unit. It will not go above 2 per unit.
Per unit. Yes.
It will
Absolutely.
be below 1.5 or something like that. It will not go above 2 per unit. and the occurrence will be in milliseconds. This is duration,
Yes.
and this like there are this temporary voltage only occurs in milliseconds or
Yes.
seconds. It will not occur in microseconds or nanoseconds.
Yes.
So that is this temporary voltage only occurs in milliseconds, and the over voltage maximum it can go like between 1 to 1.5 per unit.
Yes.
So that is the understanding you should get by looking this like looking this plot. So the second one is the switching front over voltage, or SFO, or switching over voltage. Maximum it can go up to 4 per unit,
Yes.
and it will decay, or it will decay in my system within milliseconds. So let's see, like it will not take seconds to decay. It just occurs and it will ends within milliseconds. So that is the understanding of this SFO. So the maximum voltage will be 4 per unit, and it will try to decay in my system within milliseconds.
Yep.
So the next thing is switching front, or sorry, the lightning over voltage, which is the FFO.
Yep.
So this is lightning over voltage. So this may go up to or more than 6 or 7 per unit.
Yes.
The over voltage may occur like above 6 or 7, or it can reach up to 7 per unit. So we can really say that it will only reach 7 per unit. It may go up or down, like we can't say that. But that the time taken to reach the or it will decay in my system within milliseconds.
Yes.
So within milliseconds it will just it will just decay in my system. So this is VFFO, like a very fast front door voltage. So the maximum voltage can go up to 2.5 per unit. So you may think like it just 2.5 per unit, it will not impact my system as FFO. But the issue is, look at the time taken for this. It just decay in my system within microseconds, or to be precise, within nanoseconds, it will decay in my system. So nanoseconds is so like it just happen in my system and just decay within nanoseconds.
Yes.
So you get the point, right? Like which is so most dangerous. This
Yes.
VFFO is dangerous because it will decay in my system within nanoseconds.
Yes.
So switching the how they have differentiated with what is switching or what is lightning because of time taken and because of the time taken.
Yes.
So this is important. Like even if you go to this plot,
Yes.
this is again an important thing. So this is this continuous and temporary. Like we can be this omega. This is a normal thing. This is
Yes.
normal thing. This is the transient thing. So the slow front and the fast front and very fast front. I'll just show you. This is the test waveform, like or the standard test waveform. It's like in laboratory they used to do that. A standard test waveform. See, in BFFO there is no standard test waveform they can give.
Yes.
So up to now there is no standard test waveform for VFFO. So this is a pretty much dangerous thing. Like you can't say uh, 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 this will give an impact or it will not give an impact. You can't say. So that's why we have to do just the study for VFFO. This is important thing
Yes.
because you don't have standard waveform. You don't have any reference for that. Simply you have a reference that like the time taken. TF is the time. Like I can explain with this switching SFO. So you can see, right, the TF and T2,
Yes.
TP and T2.
Tito.
The TP is the peak.
Time to the
The,
peak.
the occurrence of the peak may occurs within 20 microseconds to 5,000 microseconds.
Yes.
If I'm going to energize at 0 seconds, and within 20 to 5,000 microseconds, my over voltage may get to the peak value.
Yes.
And the T2 is like it's 20 milliseconds. The T2 is the 50 percentage of the decaying value. For example, it creates 400 kV over voltage.
Yes.
Then at T2 seconds, if you measure, the over voltage will be 50 percentage of that, maybe 200 kV or less than 200 kV.
Yes.
So that is 20 microseconds. It will decay in my system. The 50 percentage of over voltage will decay in my system. Any doubt on this plot or this waveform?
No,
Himanshu?
no.
Yeah. So the next thing is fast front door voltage. Again, the same thing. Like they have differentiated with T1 and T2. The T1 is the peak value. It may occurs in my system within zero point 0.1 microseconds to 20 microseconds.
Yes.
And the T2, which is the 50 percentage of like over voltage, will die out within 300 microseconds.
Yes.
So the time is most different. Like this is milliseconds.
30,000. Yeah.
This is microseconds. Whether like, do you know about relays, like protection thing?
Yeah, I know what relay is, but I don't know protection.
Okay, okay. Generally, the relays take microseconds. Like the time period for relay it takes like milliseconds to trip or
Milliseconds.
to react.
40 milliseconds. Something.
Yeah. So to react, it takes like milliseconds. But if there is a fast and low voltage in a system, your relay will not trip because it just dies within microseconds.
Yeah.
So that's why it's important to just to know what time it takes and what times it takes to decay at 50 percentage.
Yes.
So here they're just saying the TF is the one full cycle. I think so. Like they are trying to say one full cycle, and they are talking about the frequency.
Yes.
So the frequency is also important. Like I just show you I have a separate. I have a. Yeah. So this is also an important thing. Like I just took it from one of the book. I just forgot the book name. So like I just took it from that.
Yes.
So load rejection, like typically it will be 0.1 hertz to 3 kilohertz. It will not go 3 kilohertz, but there are some chances it may go to 3 kilohertz.
Yes.
And fault initiation, like it may be within 50 to 60 hertz or 20 kilohertz.
Yes.
But look at the transform energization. There will be some DC concept, DC component will be here. Can you say why? Like why only on transform energization they have included this DC?
That's because of the
Yes.
that's because of the current. Like.
Because of the inductance.
Yes.
Because of the inductance, there are some chances my voltage, my zero or my current will not go to zero crossing.
Yeah.
So, for example, what is the basic difference between a DC and AC? Like, if the waveform something like
Yes.
this you can call it as AC,
Yes.
and if I have waveform something like this, I can call it as DC.
DC. Yeah.
So,
Mostly.
while doing transform energization, because of the inductance in the high level of inductance in the transformer, my current will not goes to zero crossing. Like it takes some time to go.
Yeah.
So that period they used to call it as DC
Yeah.
because of the inductance in my transformer.
Okay.
So that's why they are like they have given this DC concept over here. So lightning surges or the FFO that will be 10 hertz to 3 like 3 mega like MHz, which is megahertz. So these things are important. Like if you're trying to crack any interview, like if you just remember this value, like they will just like consider you like something like that, because this is important thing. You should know on what frequency ranges our system will be or the over voltage will be.
Yes.
I'm sorry. Fine. So yeah. So these are the standard tests. So while going to lightning model, we will be seeing like something like this.
Yeah.
The lightning lightning block we will create that, and uh, the outcome will be something like this.
Yes.
Yeah. Then we can go to our modeling. We can talk about SFO.
Yeah.
Uh, SFO cases. So transformer line energization.
Yes. Transmission line. Yeah.
Just a minute. SFO cases. So transformer line energization. So this is without line arrestor or surge arrestor. I'll just show you in the thing. Um, okay, yeah. Yes. Can you see the surge arrestor over here?
Yes. Yes. I can see it.
So
Yes.
only on OHL in
Overhead
this
line.
project. only on OHL they have given the surges.
Yes.
So the thing you have to do is while doing SFO, you have to consider this surgery and you have to do the studies.
Yes.
You can't insert or you can't place a suggester over here because you don't have a suggester in cable. So by looking this, you have to say where is this suggester and how the case is to be formed.
Yes.
So in OHL, I have a suggester, so I have to do a case something like this without line arrestor and with line arrestor. The case one is repeated with surge arrestor.
Yes.
So the case 3 and case 1 are both are similar. The only difference is without line arrestor and this is with surge arrestor. So that is the difference between case 1 and case 3. I'll show you the PS card modeling for this. SFO cases and case 1 for underlying energization. So case 1 for under KV transmission line energization. So here I have used a multi-run. So when I say SFO, bare minimum I have to use the multi-run and I have to find the worst case.
Yes.
So these things I think so. Venkatji would have explained this.
Yes.
Yeah. So this BT close one and BT close two, and you have to give the output of the from the multi-run to this breaker,
Yes.
and you have to find the worst case, and you have to just disable this, and you have to give the worst case value, and you have to just do one run.
Yes.
So that is important. Fine. So here I'm going to only energize this one side, which
Circuit.
is this is double circuit. I'm just going to energize only one circuit. So which is I can show you that. So this is an OHL and this is an OHL. So a tower comes from this, and this is one circuit, and this is another circuit.
Yes.
So I'm going to only energize this circuit.
Yes.
So that's the same thing I have done here. So this circuit I'm going to here which is this is with surges. So
Yes.
I have created a model for surges, and this is with surges, and the over voltage measured over here, and you can measure the over voltage here also.
Okay.
So the voltage I've measured here because this is the like incomer,
Yes.
and either way you can measure, like you can measure here, or you can measure here also, because there will be no not a change, because there is no impedance between this point and this point, right? Just a wire or just a bus.
Yes.
So there will be no difference at all. So if there is an impedance or if there isn't any component, you can say there will be a difference. But since there is no any component in between that, you can measure either here
Yeah.
or this here. So
Yes.
that's not an issue. So this is how we used to do. This is transformer energization. So energization means I'm just going to close the circuit breaker. That's it. Only one operation. So
Yes.
normally the breaker is like no NO, which is normally opened, and
Yes.
I'm going to close the circuit breaker. Only one thing I'm going to do with this.
Yes.
So this is transformer energization. Uh,
Transmission.
I'm sorry, yeah, transmission line energization. Thank you. I'll just show you another case. Transmission line re-energization. Okay, I'll show this case too. Re-energization and energization. I'll give you the difference between that. Case two. Over here. Re-energization. Okay, let it open.
Um,
So this is again re-energization. So difference I can tell you what is the difference between that. So here in re-energization, I'll give you two operations.
Okay.
Like the first operations would be like this is normally close. Like
Yes.
this is normally in service. I'm just going to open it, which is a de-energization, and again I'm going to close it, which is re-energization. I'm again energizing this OHL. So that is the difference between case one and case two. The case one was I was only one breaker operation. I'm going to energize it.
Yes.
But the second case is somewhat different. That is re-energization, which is the normally close, which is this OHL is normally in service,
Right.
and
Yes.
I'm going to just open it and I'm going to close it. So the second one should be the output of the multi-run, not the first one, the second one.
Yes.
So you can give 100 milliseconds between that, like the first operation and second operation. 0.3, I'm going to like open it, and at 0.4, I'm going to close it. 100 milliseconds.
Yes.
So any doubts, Manchu? Here, you have any doubt?
No, the only thing is you will use sequential in this one again, right?
Yes, again, I have to do the multi-run on the second operation, not the first operation.
Yes. First operation is just any instant you can choose it.
Yeah, you can give 0.3 or 0.4 like
Yeah.
on your own, but the second operation you have to give the output from the multi-run for the re-energization. But for the energization, sorry, but for the energization, only one operation, and the first operation itself we have to give the multi-run output.
So you are taking maximum voltage and then sending in, and then VT close you are giving. So I right. So these other two are open, right? V2 and V3 in multi-run.
Yeah,
They are
the B3 you have to give to the corresponding phases. Like
okay.
for this BT close one, for the second one BT close 2, for
Yes.
the third one BT close
VT close.
3.
Yes.
So yeah. So this is the energization and re-energization. I can show you the plot for that.
Yes.
Just a minute.
No problem.
Mm, uh, can you see the can you see this word file?
Yes.
Yeah. So this will be the plot. So this is the energization. I'm going to just close the breaker with the help of multi-run.
Yes.
And if I just close it, I can get 819, which is 819 kV, which is around 2 per unit, right? 400 and another 400, 2 per unit. I'm going to get just if I energize this like this transmission line.
That's the minimum minus 189.
No, that's maximum. Like either way, this is minimum. Like you can't say that this negative that is minimum. No,
Yeah.
either way that is it will be the you can just take the value. You
Value.
shouldn't take the minus thing.
Yes.
Yeah,
819. Yeah.
819 like the 819. You should know what is the bill of this OHL
Yes.
or bill of the yeah. So here we are going to measure at the 400 kV substation. So the bill we should take the reference from the bill is from the substation, not from the OHL.
Yes.
So we can check what is the bill. I'll just show you that.
Because that is appearing on the substation itself.
Exactly. Like I have a lot of folder. I have to check it.
No problem. No problem. Take your time.
So this is the data sheet. So this is the 1.5 circuit breaker scheme. Like this is the data sheet. If you go to fine, okay. So I just give you like I have a question. whether I have to check this bill or this bill, the first one or second one.
Second one, switching.
Yeah, because we are doing a switching operations, right?
Yes.
So the bill is 1050.
Yes.
The bill is 1050, but the over voltage is um, 819, right?
Yes.
Which is way below 1050.
Yes.
So can we conclude that my system, if I energize the OHL, my system will not affect? So can we conclude something like that because it is only 819?
No, you need to divide this value by 1.2. Is that right?
Yes,
1000.
exactly right. So we have to divide the value with 1.2.
Yes.
So I'll just show you that. I'll just show you that. So I'll just show you the so this is the first case.
Yes.
So look at the this is what I'm talking about, like protection margin.
Yes.
So you have to show the protection margin,
Okay.
and that should be within 1.2. Like what they have do is uh, this is switching insulation level, which is 1050 or whatever it is. Like like in our system, it is 1050,
Yes.
and 1050 divided by this value, you should get at least more than 1.2.
Yes.
So I have a calcium in mind, like just do that. 1050 divided by 819, it gives you 1.28. So like the value should be more than 1.2. This is protection margin.
Yes. And that
So
again comes from IEC 71, right?
yes, exactly. I'll show that. I'll show that. I'll show that. So in one of the thing they have a tabulation saying that what is the bill for each and every thing. Uh, One that would be in part one. Take on the annexures. So 400 kV. 400 kV. Yeah. So this is the standard, like standard insulation level for range two. Range
Yes.
two means like after or above
Greater than.
245 kV,
Yes. Yes.
and range one is below 245 kV.
Yes.
Below 245 kV, there is no switching voltage, switching bill.
Yes.
So you can check it. Like
There will be
only
only
they are
light.
given lightning bill,
Yes.
and above 245 kV only they will give the switching bill. And our system is 420 kV, and the bill is 1050.
Yes.
So okay, you have to take that, and you have to just do, like here it is a bill.
Yes.
So here the over voltage we got it from the substation,
Yes.
and here the protection margin. So
Yes.
the protection margin should be 1.1, 1.2, like greater than 1.2. So this
That's
second
fine.
case is the look at the first case and second case.
Yes.
This first case is without surge arrestor, and the third case is with surge arrestor. The same case. Look at the protection margin.
Oh yeah.
So while presenting to the client, if you present something like that, they have a good understanding. If I use a surge arrestor in the OHL, if I'm going to energize this circuit, then there will be some like there will be more margin than without the surge arrestor.
Yes.
So which is 1.558 and 1.28. So these things you have to like include in your report so that the client can get the full information.
Yes, one silly question maybe, right?
Yeah.
When we are saying line energization, so okay, it's fine. You are energizing line. So what is the logic behind doing the line re-energization study? Well, why
Uh,
you will turn it on and turn off and turn on again? Why is that?
I'll show you the plot. Like while looking into plot, you know that why we have to do
Why
that.
we would do it? That's the question.
Fine, I'll show you. I'll show you that. Like so, the case two is transmission line re-energization, right?
Yes, it was on and we turned it off and then turned
Yeah.
on again.
So can you see the waveform for this? Like I
Yes,
just
I
do.
can see. Yes,
So like up to 0 to 0.23,
yes,
the system is like just 400 kV.
yes,
But what the thing is, I'm just going to close this off, and there will be some flux in my system, or there will be some charges will get decays, like it
yes,
just goes to zero.
yes,
But within 100 milliseconds, I'm going to just re-on the circuit breaker.
yes.
So if I do something like that, there are some possibilities. It may go up to 1000 kV.
Yes, so the question here is the this phenomena will happen automatically for some reason in real world, and that's why we are doing it, or
Yes,
for what
exactly. Yes,
reason we are
exactly.
doing.
Yes, exactly. It may occur in my system. For example, if a person is going to turn on a circuit breaker,
Yes,
and due to some reasons or due to some fault or due to some reasons like that like the circuit breaker may get trips off, and without seeing that, like if against you just turn it on, that's
yes,
then that is re-energization. Like there are cases that may happen. So that's why even IEC have said you have to do these kind of re-energization studies.
yes.
So you have to do it, and like you this will always create the worst case, and the time like difference should be 100 milliseconds. Like
Okay.
zero point 0.3 I'm going to open it, and at 0 0.4 I'm going to close it.
Yes.
So look at this three plots, like it just goes to zero, but before even going to zero we are just turning it on.
Energizing again. Yes.
Yeah,
I,
energizing.
I
So
had understanding before that like we are doing, for example, a transformer energization for transformer. So I
mm,
thought the same thing you will do, like transmission line energization for transmission, but end of the day what you care is what happens in the substation, not on a transmission line.
yes, like because transmission line is not in our scope. Like
Yeah, yeah.
only a station we have to do it, because even if anything happens to transmission line, like you can like the cost will be lesser when compared to transformer and everything in the substation.
So is
So
is this transmission line switching will do any damage on, say, for example, insulator or anything like that? No.
it may cause some issues,
Okay.
but we need some simulation to be done for proving it.
Okay.
It may cause like we can't say that it will not. It may cause, but
Okay.
but we need some like simulation proof to show the customer that it
Yes.
will happen, and we have to protect it very much on that.
Okay. Okay.
So but here in our scope, like in this project, our scope is only on the like on the substation.
Substation. Yes. Yes.
So like we just want to look only on the substation part.
Yes.
So you like, can you understand the case too? Like what happens and how the plot look like?
Yes. Yes. Yes.
So this is important. Like you should know, like before going to simulation, or if you should know how the plot at least look like. So this is how a plot look like if you go for re-energization.
Yes.
Yeah. So the case third is same with the surge arrestor, and it the over voltage is like 600. Before it was 800. It's just
Yes.
600. So this is again they are trying to show the surge arrestor. Like yeah.
How you are plotting the surge arrestor energy again?
Fine. I'll just show you that. Uh,
Well, we saw this morning modeling, but we I think missed that part.
okay. Not an issue. Like if you just go into it.
Just the output again, right? Right.
Yeah. Just
Okay.
yeah.
Yeah. Energy
Uh,
and then
only,
yeah, give it a
only
chance.
this thing this is in our scope. Like we have
Okay.
to show how much of energy is going to dissipate if I have a energization study.
Yes. Yes. I get it
So
now. Okay. I remember. Okay.
fine. Yes. So this is again that, like, and this is again re-energization with
Yes.
with surge arrest,
Yes.
because the transmission line has a surge arrest. So that's why we are including the surge arrestor in this case. Otherwise, we will not include the surge arrestor.
Yes.
So again, same thing. Yeah, cable energization, like the same thing you're going to do with cable. The same scenario
And
going.
when you do the cable energization, so again you will turn off your transmission line. Is that right?
Yes, of course. Like I'll show you that. Like I'll show you the whole system.
I think it's really going great. It's a matter of like me remembering these things now, because
Yes. Like once if you like done the modeling by your own, like you will not forget.
oh yeah,
Like
yeah,
it,
I will definitely do it, brother. I will definitely do it. I mean,
so always recommend.
this project, because once I get the license, I am going to watch the video, sitting in the night and doing everything what you guys have told me. I still do, but like I will do again, and I will prepare my own notes, and then
Mhm.
after that I can delete your stuff from the system.
So this is like only the thing is I have only took the OHM, like sorry, cable.
Cable.
The remaining thing I'm not going to worry about that.
Yes.
So yeah, it depends on how you're going to model it. So let's try to say if you want to model something like yes, you can model, or if you want to model the whole system,
Yes.
yes, you can model it. So it depends on you how you're going to take the system and how you're going to present to the client.
Okay.
So this is kind of a simple model, like it will not take much time. So that you can just like that you can finish and you can take the other case and you can finish it. So that's why we have modeled something like this.
You
The
don't need to
same
show
thing.
your client like how you model PSCAD and what multi-run
No,
use.
some clients will not ask that. Some clients will ask the PSCAD file.
No, no, PSCAD file they will definitely ask.
Yeah.
That's how it works here. But
Mhm.
I mean you don't need to put in the report.
No, but like we can show the overall
Yeah,
diagram or overall
yeah,
the SLD for that, but
yes,
we don't need to put our in the report that each and every case how it look like.
yes,
We
yes,
don't want to do that. But
yes.
like if you want to give the model, yes, you can give it, and if they know how to like extract from
Ex-
this, or if you know about PSK, they can easily look into it. So this is how the same cable energization, the same concept. Like we have used a multi-run and only one breaker operation, since it is energization. I'm sorry, this is transformer energization. Like I have to show the cable energization. Yeah, oh yeah. So this will be a detailed model. Yeah. Yeah. So this OHL is one. So you can see it,
Yes,
right. It is switched off,
yes.
and this is one. This is one, and only this OHL I'm going to like talk about.
Yes.
So
Cable.
this cable. I'm sorry, this cable.
Looks
So
like
the
you are
same thing.
hungry.
No, like I always had this confusion.
Okay.
So this is from the multi-run again, and this is the cable energization. So you can just give only one operation and you can just do it.
Yes.
So the basic thing is either way this is cable or OHL, but this is the basic thing. If you're going to energize, then there will be one operation, and the output or the you have to use the multi-run. You have to do it.
Yes.
So while in SFO or in TRV, in lot of cases, this multi-run comes into picture. So if you
Yeah.
have any doubts on multi-run, please try to finish it up because it's so important. So
No, no,
this,
I don't have any doubt. The only thing is this one yesterday which we discussed. I didn't do that, like random flat and this bit close another. I need to find out a time to go through it, and
uh,
then I will ask question if I have. Yes.
fine,
The
fine. Like
previous one
just
which
try.
you explained, it is clear.
Mhm.
It is no
Yeah,
issue
fine.
with that.
You can use that also, or you can use this. Like both the way, like that's fine. That's fine. So
Yes.
yeah, so multi-run is important. So you should have a clear understanding of that. So this is case 3, and we have 17 cases for SFO. The same thing like we used to do for transformer deionization for 220 kV, for 400 kV, and another one thing, remnant flux. We used to call this is one of the like a case we have to do it. So the modeling will be different.
Yeah.
If you have let's say if you have the latest version, which is 5. Do you have the latest version with you right now, the free version?
Yes, I have. Yes.
Just share your screen, and I'll let you know like how to do it in like in the latest version, because I'm using 4.5, so the modeling may be different, but in latest version they
Transformer.
have given some.
The transformer energization, you mean?
Yeah, transformer remnant flux, like
Or
remnant
remnants
flux.
color? Okay.
Yeah.
Yeah, I can open it. Yes. I don't think I have any appropriate example, but you can.
But I'll just show you how to.
You want
Uh,
control?
no,
Okay.
don't. Like I'll just guide you. Just open any one transformer in the
Yeah.
any one. Yeah, you can just open the transformer.
Yes.
This is configuration page. Let's go to next page.
Winding rating and
Now
saturation.
saturation.
This one here, massive.
No, just go to two winding transformer. Like it has that 200.
So
Sorry. That would be, yeah, no, just two
winding
winding transformer.
to wind.
To the left. Yes. Just open it. Yeah, you can open here itself, like not an issue.
Okay.
There is some, yeah, magnetic characteristics of the material. No, not this. It is a UMAC. Okay. Here. Yeah, here you can see, right? Remnant flux core 1, core 2, core 3. So yeah,
Oh, this
just
one.
give escape. Yeah, just give escape. No, not that one.
Oh, this one. Winding current. Oh,
No, no, not this one. Like go to
this.
saturation. Yeah.
Oh, yes.
So here you can give what is the remnant flux core 1, core 2, and core 3. So
Okay.
I let you know like what is remnant flux, or how to model in 4.5.
Okay.
I can teach you that. But after even in 4.6 they had to update something like this. So there
Okay.
is no extra model needed for, like, just like that you can give the value over here and you can
Yeah.
just simulate this.
Okay.
So that's the latest version will be advantage for that. Like the remnant flux will, you can just like give on each core, and you can just do the simulation. I'll show you how to do it uh, in PSCAD 4.5. I'll
Okay.
just
Okay.
I'm sharing my screen.
No problem.
Remnant flux, yes. Cable remnant flux over here. Yes. So this is the model we have to do. Like in 4.6 or 4.5, sorry, in 5, you can model the core over here itself. Like if just to go to saturation, you can model it. But what 4.5 you have to do? You have to separate each and every individual phases,
Yes.
and you have to inject some current,
Okay.
and you have to do it like we can have a separate session for this. I don't want to confuse with the cases. Like we can have a separate session how to what is remnant flux and how to do it.
Well, how to do
So
it looks like simple, but what it is will be important because
yeah, that is
you just model three current source and you just took three control and you are just controlling using these three button and plotting it as simple as that.
yes. So like why you have to do something
But
like this, and
yeah,
what
but
is
I
remnant
don't
flux?
that I don't know.
And that's not an issue. Like we can, like not next class we have lightning to talk about. Next week we can talk about this. So what is remnant flux and how to model in 4.5, and
Yes.
what are the things we have to refer from remnant flux, and we will be using some control or something like this. So
And
since we are using this
after lightning, what you are going to plan to teach?
so tomorrow we are going to only talk about like lightning. And next week we are going to talk about TRV, which is transient recovery voltage. Like fully, we are
Yes.
talking about breakers and VFFO. So only like 2 or 3 topics are left behind in PSK.
Okay, because I was thinking is okay, if you are doing next week that, then okay, then last week we can do the solar, because that is important for me. That's it. That is what I am going to face just now.
Okay, okay, yeah. We can plan after the
Solar and solar maybe not that common like here, but I am expected to do at least one solar just now. Not like just now, but yeah, in maybe May end or maybe June or something. I don't know, to be honest. But wind is a lot here, so yeah, that two things are like quite important as well.
Fine. Not an issue. Like we can talk about solar and we can. That's not an issue.
Okay.
Like once we can complete all the studies in PSCAR, we can go for that. That's not
Yes.
an issue. Yeah. So this is like the remnant flux is still incomplete. Like I just want to like talk about the cases only. So we
Yes.
can we
That
can.
button is easy. Yes, I have done somewhat similar before. Like, put the
Mhm.
each controller different and then create the control panel to
Ah,
adjust the. I have.
okay. Yeah. Fine. Yeah, this is kind of like a simple thing, but the thing is, like this will just reset if you just close this. Like
Yes.
if you assign some values over here, it will just reset. So
Okay.
that's the thing here.
No
Fine.
problem.
We can discuss on next like next week.
Yes. Yes.
So the next thing is cases here. So transform energization, the same old thing. I'll share you this. Like you can just go through this and you'll get a good understanding.
Okay.
Yeah, this is again transformer de-energization. Like I just want to explain this. This is uh, this is kind of re-energization, but there are simple difference between that. I'll just show you.
Okay.
Case 15. Transformer KV line cable re-energization transformer.
That's 15 number.
Okay.
15 was that.
Okay, yeah.
Like,
This is 220 kV side. Yeah, yes.
yeah. Yes.
What's the timing in your place? Like now here
It's
it's
4 o'clock in
uh,
the afternoon.
fine. Then
Yeah.
so
Yeah.
this is transformer de-energization, not re, which is a de-energization. Like there are difference.
Yes.
So what we are going to do is the same thing, like two operations. But
Yes.
the thing is, which is normally opened,
Yes.
I'm just going to close it and I'm just going to open it, like which is a de-energization. So I'm not going to re-energize it. I'm just going to de-energize it. So
Yes.
I'll show you the plot how it looks. The plot how it look like.
Okay.
Yeah. Wait. Case 15, right?
Yes.
Case 9, case 10,
1515.
case transform energization and transform energization, transform energization, again transform energization. Yeah. So this is 400 kV side, and this is 200 kV side. Like this is how a plot look. So like this is normally like it has some voltage, and again I'm going to open this and I'm going to close this.
Yes.
So this is what I have explained, right?
Yes.
Just close all the things. So first is normally open, and I'm going to close this, and I'm going to again open this at B2, like at uh, the output from the multi-run. So Here if you measure like V trafo HV, then you get the voltage. So this is very basic on SFO, like the cases what we'll do, and generally these are the cases. If you take SFO, these are the cases they used to do. If they have OHL, if they have a cable, or if they have a like transformer, these are the typical cases they do. And there are some, if you have a reactor in your system.
Yes.
So in our system we had a reactor, right?
Yes. Yes.
So there are separate two cases for reactor also.
Okay.
Reactor, yeah. So reactor energization. So reactor energization with the OHL and with the with only the cable.
Okay.
So we you have to do, if you have a reactor, you have to do the same thing, the same breaker logic, everything is same.
Okay.
You have to instead of transformer, you have to get the reactor and you have to do it.
And in this switching diagram, I remember you model reactor just as an inductor, not as a saturable reactor. Is that right?
Yes, I'll show you. I'll show you the, how to model it. That's important. Cable reactor. Yeah. Okay. Yes. So this is a saturable reactor. So you have
Yes.
to do with a saturable reactor, not just an inductor. Like you have,
Okay. Okay. I have the another file. Yes. Yes. Okay.
because this is an SFO and the voltage will not be like 1 per unit always, right?
Yes.
So there is some knee point voltage, or the voltage may differs after 1.15. Like you can see, right? If I have 1.15 at the fourth point, the current just goes to 1.12.
Yes.
So
Yes.
it's not behaving relatively.
Yes.
So that's the difference. So if you have more than 1.15 voltage, a reactor will not act like as the voltage goes. It acts differently.
Yes.
So you have to account those things also, right?
Yes.
So then you have to include that saturable reactor modeling, and you have to do it.
Okay. The
So
only additional thing there is I just need to enter the VI characteristics.
yeah, yeah.
Yes.
So since why we have modeled this as an inductor is because we are not going to take account of this reactor.
Yes. Yes.
So this reactor is in our scope.
Yes.
So that's why we have modeled this as detailedly.
Yes.
It's because like we have to finish this project fast, so we just did something like this. So
Okay.
only the things which you are going to talk, or like that things which are in scope, we used to model as detailedly, because this will either way the circuit breaker is going to get closed.
Yeah. Yeah.
So all circuit breakers are like one, and only some of the circuit breakers is open.
Yes. Yes.
So this is this is the reactor circuit breaker, and we are given the multi-run also.
Yes.
The
Yes.
same.
I understand it. I
Yeah.
just need to put these all things together, somewhere
Mhm.
and practice them. Yes.
Yes. So fine. So this is all about SFO and yeah, TOB.
Yes.
So I'll share this cases, and I'll share the output, like the table which I have shown, right?
Okay,
Uh,
that would be great. Yes. Yes. That
yeah.
will be a
I
reference
just
for me. I
yeah.
will try to
You
get
can
those
just
results.
try this, and if you just close to this value, or if you get these values, then you can say this the modeling is right, and you can just move on to SFO and you can do it.
Yes, yes. At the moment, I will first try to model the surge arrestor and stuff from this morning, and then I will try to do one of the cases here just to get some confidence, and then
Okay, okay,
then over the week I will do more cases on more
fine.
practice if I get time. If not, then we'll see.
Yeah. So
Yeah.
the things which I want to share is the documents is this one, and the
Yes.
cases and the
Yes.
results of that.
Okay.
And apart from that, I'll share this frequency, and yeah, I'll share this. What is
Okay.
the frequency range of all studies? That would be
That.
important. You
Yes.
can use it.
Yes. Yes.
Yeah.
If
So
I do like some substation, some like substation project later on, I can build the the things on my own, but like before presenting to them someone, or before like you know sending it to some, I know they Arcadis said like I got some like external expert or something, but I think I will give you guys a look, like if you can comment on something, or you think like if I am doing something right or wrong.
Yes. No, that's not an issue. We can do it.
Yeah.
Not an issue. Yeah.
Yeah.
So,
It's just to see like how your student is going.
ah, okay, okay, fine. Okay. So this is for today. Like we
No
have
problem.
we have
No problem.
we have we have talk on we talk about TOV and SFO and how to do the cases and how to check the plot and how to verify our case whether the results are right or wrong. So this
Yes.
is
Yes.
what we have seen. And
Yeah.
tomorrow we are going to talk about lightning studies and how to model the lightning block
Okay.
with the current source and how to the calculations behind the lightning. So direct strike
Okay.
and the backflash over.
Yes. Yes.
Yeah.
Yes. No
Yeah.
problem. And
Any
that
doubt?
will no doubt, no doubt. And
Okay.
that will be again afternoon 13:30, right? Tomorrow.
Yeah, 1:30. Yeah, 1:30. That will be 1:30. Like today, a power cut issue, so that's why we had.
No, no, it's fine, mate. It's fine. It's totally fine. I understand it. It's not a big deal. You know,
Mhm.
it's not a
Fine.
problem. So your
Okay, then
dinner is ready?
I don't know. Like I have to check it. Like what they are doing, I don't
You,
know.
okay, you're not married yet? Or you
No,
married?
no, not married.
Oh, that's why you're a happy man. My wife is staring me.
Okay.
Okay, so what is in the dinner? Like
I
dosa
don't
or
like chapati.
rice
I
or
think. Uh,
chapati? No one eats
yes.
chapati in South, do you?
Yeah, in like they don't do often chapati in south, but in north area they used to do a lot of chapatis.